in the standard model of particle physics, all particles are classified as either a boson or a fermion. So when we want to talk about the standard model, one of the first things that one needs to know is what is a boson and what is a fermion. So here we have one of the standard tables that you'll find if you just Google standard model of particle physics, which is really summarizing all of the fundamental particles that we understand under the framework of the standard model. And we see that there's these different color schemes here. There's purple, green, red, and yellow. I'm sorry if you're colorblind and you can't see the difference, but I'll highlight these different colors in future videos. We see these different colors are telling us different ways that we're categorizing these particles. And in this video, I really want to talk about the first categorization, which is of bosons and fermions. So on the left-hand side here, so I've added this box, which hopefully you can clearly see. On the left-hand side, our quarks and leptons are our fermions in the standard model. So these particles comprise our fermions. And then the right-hand side are our bosons. And so as we can see, all particle is classified as either a fermion or a boson. So what's the difference between these two? Well, if we look a little closer, so let's look at the bosons first. In each box here, for instance, if you look at the gluon box, you see 3 values. The top value is telling you the mass of the particle. The second value is telling you the electric charge. And then the third value is telling you the spin of the particle. So what we'll notice if you look at the gluon, the photon, the Z boson, and the W bosons, they all have spin 1. And again, that really means 1 times h bar. So they all have spin h bar. And then the Higgs boson has spin 0. And so bosons are defined as particles which have integer value spin. So gluon, photon, Z boson, W boson, they all have spin 1. Again, that means h bar actually. And the Higgs boson is spinless. It has spin 0. So that's also an integer. If one day we find a graviton, which currently is not described under the standard model of particle physics, it would have spin 2. So a graviton would also be a boson. These are our force-carrying particles. So the gluon carries the strong force, the photon carries the electromagnetic force, and the Z and W bosons carry our weak force. So more about that later. But for the purposes of this video, you really want to think about the bosons as being with integer spin. And an important property of bosons is that they're okay being in the same state as each other. And so what I really mean by that is the quantum state as each other. They're happy to hang out with each other. I think this might be a little more clear when we talk about fermions, which we'll see, we'll learn are not okay as being in the same state as each other. So let's do that. Let's talk about fermions, which were that left-hand side of our table. So these are our fermions under the standard model. These have half integer spin. Now, a fermion doesn't have to exactly have spin 1/2. It could have spin 3 halves, 5 halves, 7 halves, etc. But all of the particles that we know about in the standard model have spin exactly 1/2. And so all of our quarks have spin 1/2. All of our leptons have spin 1/2. The most familiar particle of the standard model, which is likely the electron, it has spin 1/2. Now, fermions can never be in the same state as each other. And this actually ultimately is the reason for all of chemistry, really the way chemistry works the way that it is. So when you first learn chemistry, you learn that atoms are made up of a nucleus with electrons orbiting the nucleus. And you learn that the electrons orbit the nucleus in these specified ways where they fill up these orbitals. Why do the electrons fill up these orbitals? Why don't, say, all of the electrons hang out in the first orbital? Or why don't they crash into the nucleus, right? Why are the electrons filling up these orbitals? Well, that's really because they're fermions. The reason you can't just have as many electrons as you want in any given orbital is because of their fermionic nature. So that's what I mean when I say they cannot be in the same state as each other. An electron being in a particular orbital with a particular spin direction, that's a quantum state of that electron. And you can't have more than one electron in any given quantum state. And so again, that's really why chemistry works the way that it does. Things would be really boring if fermions behaved the same way as bosons. So if bosons were orbiting a nucleus, you could have as many bosons as you want in the same quantum state, and there's no problem with that. And so fermions and bosons are really fundamentally different for this reason. So those are the main things that you need to know about when we talk about bosons versus fermions.